Hello, myself Professor H.K. Bangare, Department of Electrical Engineering, SND College of Engineering and Research Center, EULA. So we are discussing about the basic electrical engineering of first year engineering subject. So we are discussed today on DC circuits and part 4. Let us proceed with Kirchhoff's current law. Now Kirchhoff's laws are stated by Kirchhoff's for analysis of the electrical network. So what is Kirchhoff's current law? It is denoted by KCL. So at any moment, the algebraic sum of flowing currents through a point or junction in a network is zero. Or in any electrical network, the algebraic sum of the currents meeting at a point or a junction is zero. So this law is also known as point law or current law. So this current law or Kirchhoff's current law is associated with the currents, and the currents in the network which are entering or leaving at a junctions. So at a junction or at a node, so at particular junction or particular node or a particular point of the network, whatever the number of currents entering at that point, the sum of all that entering currents at that point is always equal to the sum of the currents those who are leaving that point or a node. Or in other words, we can say that the currents entering is equal to currents leaving that junction. Or in other words, we can say that the sum of the algebraic sum of the currents at a junction is always zero. So that is Kirchhoff's current law. Similarly, Kirchhoff has defined a Kirchhoff's voltage law, that is KVL, and KVL, it is nothing but the algebraic sum of the voltages around any loop in a circuit equals to zero. Now Kirchhoff's current law is related to currents at a junction, while Kirchhoff's voltage law is related to a potential or voltages in a particular loop or a mesh. The algebraic sum of all the voltages around any loop in a circuit equals to zero. When we will traverse from a loop, all the loop elements, in that time, whatever the voltage drop across each element and whatever the number of batteries or energy sources in that loop, the algebraic sum of all that is zero around that closed loop, and that is nothing but is a result of conservation of energy. So it is a Kirchhoff's voltage law. Now today we will discuss in detail the Kirchhoff's current law in this lecture. So the terminology in voltage or in network is very first you must know what is a node. A point where two or more circuit elements are connected, that is nothing but a node. And a branch is nothing but a path that connects two nodes. So here it is a single branch, okay, which connects the two nodes, that is a branch. Okay, this is not a single branch. Okay, this is one branch, this is another branch. Okay, this is another branch. So here another node may be there, here another node may be there, here another node may be there. So it is a single branch. Okay, though it is connecting the two different nodes, but then also it is a single branch. Use one node as a reference, the common or ground node, and label it with a symbol as a negative. The voltage drop from node X to the reference node is called the node voltage Vx. So the voltage across a circuit element is defined as the difference between the node voltages at its terminals. Voltage across a circuit element is defined as the difference between the node voltages at its terminals. Here, suppose R1 is one of the terminal. So here VA and VB will be the terminal voltages of these elements. Okay, so the voltage across the circuit element R1 is defined as a difference between the node voltages, that is VA minus VB. Okay, so that is the difference or voltage across R1. Similarly, this is R2, across this R2 it is plus. Here VB it is common, so it is negative, it is zero, means it is VB. Across this VS source, it is VA. Okay, common node is there. So in this way, the voltage across the element is defined as the difference between the node voltages at its terminals. Now, a Kirchhoff's current law. Now here consider a node connecting several branches. So here is the node. To these several branches are meeting at this junction or at this node, and the different values of currents are flowing in a different direction to this node or through these branches, and all that current will passes through the node. But the resultant current at this node is always zero, because let us assume that current I1 is flowing through this branch, current I2 is flowing in this branch, and these two currents I1 and I2 are incoming currents or entering currents in the junction or in the node, while I3 is flowing in this branch and I4 is flowing in this branch. Both are outgoing or leaving currents. So according to KCL, the sum of the currents entering at a junction is always equal to sum of the current leaving to that junction. So here I can say that I1 plus I2 is equal to I3 plus I4, and it is nothing but your Kirchhoff's current law. Now here again one more example I have taken. So here current I1 and I5 are entering the node A, while current I3, I4 and I2 are leaving the node A. So according to Kirchhoff's current law, sum of the currents entering the junction, that is I1 plus I5, that should be equal to the sum of the currents leaving that junction. The leaving currents are I2 plus I3 plus I4. So this equation I will formulate it. I1 plus I5 is equal to I2 plus I3 plus I4, and this is the KCL. It is the nothing but your Kirchhoff's current law. Here another example is there. I1 current is entering the junction. I2 and I3 currents branches are there, and through that I2 and I3 currents are leaving that junction. I1 is magnitude 6 ampere. This 6 ampere will get divided into these two branches at this node, and I2 is 2 ampere, I3 is 4 ampere, and hence here resultant current or sum of the currents at a junction, it should be 0, means your 6 ampere is equal to I2 plus I3, that is 2 plus 4, and it satisfies, that is sum of the currents at a junction, means incoming currents if I take positive, outgoing current should be negative. So 6 ampere minus 2 ampere minus 4 ampere is equal to 0, and that satisfies my Kirchhoff's current law. Now this Kirchhoff's current law we can formulate in different ways. So formulation 1, sum of the currents entering node is equal to sum of the currents leaving the node. Second type we can formulate is that algebraic sum of currents entering at the node is equal to 0. So current leaving are included with a minus sign. Then the third category is algebraic sum of the currents leaving node is equal to 0. So currents entering are included with a minus sign here. So ultimately the sum of the currents or the currents at a node is always 0. So the charge stored in a node is 0. Always it is 0. Then the implication, we will see the major implication in KCL. So KCL tells us that all the elements in a single branch carry the same current. No doubt, if a branch is same and though the number of different and different elements are there in that branch, then also the current flowing through that element is the same current. So we say that these elements are connected in series. Okay, so here this element and this element, they are in series, and suppose these are connected to this junction point here, then I1 and I2, it should be equal. I1 or the sum of the currents entering, that should be equal to sum of the current leaving. So current entering is I1, current leaving is I2. This I1 should equal to I2. So the current entering the node is equal to current leaving the node. I1 is equal to I2 according to KCL. Here another one example is there. Here the 1, 2, 3, 4 branches are there. They are meeting at a junction. This is node. This branch carries 5 milliamp current. This branch carries minus 10 milliamp current. This is outgoing current I1, and this is the outgoing current 15 milliamp. So current entering the nodes are minus 10 ampere is entering and plus 5 ampere is entering, and current leaving the nodes are this I current is leaving and this 15 milliamp current is leaving. Okay, so if according to formulation 1, so what is my formulation 1? So formulation 1 is sum of the currents entering the node is equal to sum of the current leaving the node. Means here the sum of the node entering the currents are minus 10 plus 5 milliamp. How much it is? It is 5 minus 10, so it is minus 5 milliamp is equal to sum of the currents leaving. 15 milliamp is leaving and I is leaving. So 15 plus I is equal to 5 minus 10. That is 15 plus I, that is equal to minus 5, and hence I will get the value of I also. I can calculate the unknown current also. Okay. Second formulation, the algebraic sum of the currents entering is equal to 0, and that time whatever the leaving current, that will be considered as negative. So I can write that minus 10 milliamp plus 5 milliamp minus I minus 15 milliamp is equal to 0. And third category of formulation, I can write that the sum of the currents leaving is equal to 0. That time you consider the incoming current as negative, means I is equal to I plus 15 milliamp minus 5 milliamp plus 10 milliamp is equal to 0. And these three ways are formulation are nothing but your Kirchhoff's current law. So the sum of the currents entering and leaving, entering or leaving a closed surface is 0. So circuit branches can be inside this surface. That is, the surface can enclose more than one node. Here it is the surface. Okay. So the circuit here at this surface, different several branches are coming out and leaving the junction and entering this surface. Okay. So the circuit branches can be inside. इसके अंदर भी कुछ branches हो सकती हैं inside this surface. But this surface can enclose more than one node. Right? But for this whole surface, I can say that I1 plus I2, that should be equal to I3 plus I4. Whatever may be the number of nodes and branches inside this surface may be. But as a whole surface, I can consider it as one node. And at this surface or at this node, two currents are entering I1 and I2. And that should be always equal to I3 plus I4. Okay? So there may be any complicated circuit inside this surface. Okay, this whole surface we will consider as a one node. Okay, and for this node, we apply the Kirchhoff's current law, and according to Kirchhoff's current law, the current entering that should be equal to current leaving the junction or a node. So this could be a big chunk or a circuit. A black box, you may say, it is a black box. We don't know how many numbers of elements are there inside this black box or this surface. What a complicated network may be there inside it, but we are assuming that as a single node, and in that current entrings are there and current leaving are there, that only will look and will apply the KCL to it, and KCL will be satisfied. Here another example is there. Here 1, 2, 3, 4 branches are there, and here 50 milliamp current is entering, and this current is entering at a node, and when this one incoming is there, and 1, 2, 3, 4 in 4 branches this current is divided, but the leaving point is only one single branch, single node. Okay, so here is leaving. So no doubt at this I, means this I is always equal to 50 milliamp. Though in these particular branches this 50 milliamp is divided into 4 numbers. Okay, but the current leaving this whole circuit is always equal to 50 milliamp. Similarly, here 5 microampere current is flowing in it. Okay, so it get divided into these 2 branches. Again, it is divided into these branches. Okay, and I can say that the I, and it is 2 milliamp. Okay, so this whole, as I consider if a node, then apply the KCL to it. It also satisfy the current entering at this node is 5 microamp, so that will be satisfied here in 2 branches. Again, here it will get satisfied. So in this way, in generalized KCL can be applied right to a number of nodes in the circuits. So today is sufficient for KCL. In next lecture, we'll see the details of the KVL. So goodbye. Thank you.